We have started our discussion on AC power analysis, and in the previous lecture we discussed the power of average RMS, which is the effective value also, and we also discussed the maximum power transfer theorem in AC circuits. Let us solve one problem to understand more on the RMS power and the other powers. So given the waveform, you have been given one waveform. Determine the RMS value, that is the root mean square value, or the effective value, the other name is there, of the current waveform which is shown. So on the y-axis you have the current with respect to time t. If the current is passed through a 2 ohm resistor, so this current is passing through a 2 ohm resistor. Find the average power absorbed by the resistor. So you have to determine the RMS power and you have to determine the average power also. So first we will try to determine what is the time period of this waveform. So we can see that the waveform is starting from here 0 and it is completing one full cycle at 4 seconds. So the time period is 4. After 4 seconds, if you see from 4 to 8, the cycle is repeated. So the time period of the AC waveform is 4 seconds. Now over a period, we can write the mathematical equation for the current, splitting it into two zones from 0 to 2 second and from 2 second to 4 second, because at 2 second you can see that the waveform has become discontinuous. So till 2 second you have a straight line whose equation you need to write it, and from 2 to 4 second there is also a straight line whose equation you can write it. Once you have written the equation which is a function of time t, I of t, then you can find the RMS value. RMS value, the formula is you have to find the average, that is the mean value which is divided by the time period, and square of the instantaneous value of the current that you have to take. So this is the instantaneous current which is a function of time, and then you have to take the root, so you are taking the root of this. Now this current equation which is a function of time, you have to split it as per the mathematical equation that you have used it here, and then on integrating and substituting the definite integral from 0 to 2 second and 2 second to 4 second, you will be getting the value of the RMS quantity. So you can see that instantaneous quantity is a function of time, whereas the RMS quantity is only a constant which is not a function of time t. Now the power which is absorbed by the 2 ohm resistor, which is the average power P, is given by the formula I RMS square into R. If you remember in DC circuit when we discuss, the power is basically I square, into R, right? So in AC circuit, this current is substituted to I RMS. So that is the reason we are trying to calculate the RMS current of any AC waveform. So then we are getting 133.3 watt as the average power which is absorbed by a 2 ohm resistor. Next problem. Now given the waveform which is a voltage with respect to time t, this waveform is a half wave rectified sine wave. So what is a rectifier? A rectifier is a device which convert the AC waveform to DC waveform. Okay, so this is a rectified sine wave. Find the RMS value and the amount of average power which is dissipated in a 10 ohm resistor. So for this AC waveform, you have to determine the RMS value first, and then you have to determine what is the average power which is dissipated in the 10 ohm resistor. So similarly to the previous problem, first you have to determine what is the time period. So you can see that from 0 to pi you are having one waveform, and from pi to 2 pi there is no waveform is there, because it is a DC waveform which will be there only for one cycle. So from 0 to pi you are having 10 sine t as the waveform, whereas from pi to 2 pi there the waveform is 0 because you do not have any cycle in that. Now the RMS value, you know the formula for RMS value. Here we have taken the square to make the calculation easy, so that we can remove the square root. So we can substitute the value of the voltage, which is the instantaneous value, in two time zones which is from 0 to pi and from pi to 2 pi. And then we can apply the concept of the trigonometry, that is sine square t is equal to half of 1 minus cos of 2t. Then we can substitute this sine square t as 1 minus cos of 2t, and then we can integrate it from 0 to pi. So on integrating, we are getting 25 volt as Vrms square. So the Vrms will be the square root of that is 5 volt. Now the average power which is absorbed by the load of a resistor of 10 ohms is basically Vrms square by R. If the current is given, then you will be finding Irms square R. If the voltage is given, then you can go by the formula Vrms square by R. So the power is equal to 2.5 watt. So this is the average power which is absorbed by the load. Now next topic that we are going to discuss is apparent power and power factor. Let us see from the basic. So we have the instantaneous value of the voltage and instantaneous value of the current, which are time dependent quantity, having the maximum magnitude is Vm for the voltage, maximum magnitude of the current is Im. Theta V and theta I are basically the phase angle of the voltage and the current, and the frequency is constant, which is given by omega. Now we have calculated that the average power P is given by the equation half Vm Im cos of theta V minus theta I. This derivation we have already done. We have also done one derivation that power is equal to Vrms into Irms into cos of difference of the angle between the voltage and the current. Now one term we are going to introduce today is what is this product of voltage and current RMS that we can substitute as S. So S is equal to Vrms into Irms, and that is known as the apparent power. So apparent power is basically the product of RMS value of the voltage multiplied with RMS value of the current. So if you see the average power, which is a product of two terms. So the product Vrms into Irms is known as the apparent power, and apparent power is denoted here by S. The factor cos theta V minus theta I is known as the power factor. So here you have the cosine of the angle difference between the voltage and the current. That is known as the power factor. Why the term apparent power name has been given? Apparent power is given because it seems apparent that the power is the product of voltage into current. If you remember in DC circuit when we discuss, the power is the product of voltage into current. This is for DC circuit. Now for the AC circuit, we want the same value of the power, or the same formula for the power rather. So we can write that the apparent power is the product of RMS value of the voltage and the RMS current. So these formula of the AC power and the DC power look similar. So that is the reason the name has been given as apparent power. Apparent power is measured in volt-ampere. If you see, the unit will be voltage multiplied with the current. So that unit is volt-ampere. And it is to distinguish from the other power, that is average or real power. Whereas the average power or the real power unit is in watt. Okay, so your average power unit is in watt, whereas the complex power unit is in volt-ampere. Whereas the power factor is dimensionless. There is no unit for power factor. Its value will range from 0 to unity. So from 0 to unity, you will be getting the power factor. So power factor you can define as the cosine of the difference between the voltage and the current, or otherwise you can say that the real power divided by the complex power, you will get the power factor. So power factor is basically the ratio of average power by the apparent power S. Okay, apparent power S, which is the product of voltage into current. So you can see that on the numerator you have the power which is Vi cos phi. Okay, we can write the real power as Vi cos phi, and the apparent power, we can write the product of voltage into current. So these will cancel out each other, and then the power factor will be equal to cos phi. So power factor is equal to cos phi, where phi is the angle difference between the voltage and the current, and its value lies between 0 to unity, which is very important. The angle difference between the voltage and the current is known as the power factor angle. The reason why is that if we apply the cosine of this, then we'll get the power factor. So it is known as the power factor angle. The difference between the angle of the voltage and the current is known as the power factor angle. If you have a pure resistive load, means there is no inductive effect or capacitive effect in the load, then the power factor will be unity. Whereas if you have a pure reactive load, that is either the inductor or the capacitor, then the power factor will be 0. That is the reason we say that power factor lies from 0 to unity. Unity means the load is purely resistive, whereas the 0 power factor means the load is either inductive or capacitive. In between this, the load will be either lagging power factor or leading power factor. This we will discuss a little bit more in detail. The power factor angle is equal to the angle of the load impedance if the voltage across the load and current through is given. Means if you have a load impedance Z, if you have a load impedance Z and voltage across it is given to you, and the current which is flowing through the load impedance is given to you, then we can find the power factor angle is basically the angle of the impedance. So if you have this power factor Z, which is a complex quantity, Z magnitude, and the angle theta, this theta is basically the power factor angle. Now we'll see how it is. Let us denote the Z, that is the load impedance, is equal to the ratio of the voltage by current. So you have the ratio of voltage by current, and these are phasor quantity. Now the phasor quantities are written as the maximum value of the voltage with angle theta V divided by the maximum value of the current angle theta I. So we can take the division of the real part and we can take the angle difference of the voltage and the current. Now the V RMS we can write as V by root 2, that is the maximum value of the voltage, we can write Vm by root 2, then it is equal to V RMS angle theta V. Whereas IRMS, if you see it, whereas IRMS is equal to IRMS angle theta I. Then the Z, which is the load impedance, is equal to VRMS by RMS. So it will have VRMS by IRMS. This is the magnitude, and theta V minus theta I is the angle. So if we can have the load impedance Z, which we can write as the magnitude of the Z and angle theta, this angle is the power factor angle. So if we need to find what is the power factor, so power factor is basically cos of this angle theta. Let us solve one problem to understand the power. You have a series connected load. Series connected load is there, which is drawing a current which is given as the time dependent quantity as the instantaneous value of the current. The voltage which is applied through the load is also given, which is instantaneous as a function of time t. Find the apparent power and the power factor of the load. Determine the element values, because here it is said that it is a series connected load, but what type of element is that, it is not given. Whether it is a capacitor, inductor or a resistor, that it is not given. So you have to determine what is this element that is forming the series connected load. So we have been given the current and the voltage is instantaneous. Now first we have to determine the apparent power. So in the problem we have been asked what is the apparent power. Apparent power is the product of RMS value of the voltage into RMS value of the current. Now this 120 is basically Vm, because we know that any AC waveform is written as Vt is equal to Vm cos of, this is omega and this is theta V. So here the RMS quantity is equal to Vm by root 2. So Vm is equal to 120. So if we divide it with root 2, we will get the Vrms. Whereas the I maximum is equal to 4. It means if we divide it with root 2, we will get the IRMS. Then the product of the voltage and current, we are getting 240, and the unit is in volt ampere. The power factor is basically cosine of the difference between the voltage and the current. So we see that the voltage is at minus of 20 degrees. So if we have 0 degree as the reference, and angle is always measured in anti-clockwise direction. So here you have the minus 20 degree with respect to the reference. So minus 20 degree, and you have a plus 10 degree as the current. So you can have minus sign here. So that will give minus of 10 degree. Then you find the cosine of this value. You will find 0.866. That is a leading power factor. You know the power factor will lie between 0 to 1. So if you are having the power factor as positive, it means that the power factor is leading. If you are having the power factor as negative value here, if you have a negative value here, then the power factor will be lagging in nature. So this positive and negative is only to decide whether it is lagging or leading. The values will be between 0 to 1. Now, the power factor is leading in nature because the current is leading the voltage. If you see the current, it is leading the voltage because of this angle. The angle of voltage and current, you can decide whether the current is leading the voltage or voltage is leading the current. We can easily see that current is leading the voltage, so power factor is leading in nature. The power factor may also be obtained from the load impedance. Okay, how? Let us see that. We know that the impedance is the ratio of the voltage by current. So here we can convert these into phasor quantity, that is 120 angle of minus 20 degree. Now the current we can convert in phasor quantity, that is 4 angle 10 degree. So we will be having the impedance as 30 angle minus 30, because you have minus 20 and minus 10 degree. So it will have minus 30 degree here, and 120 by 4 you will be getting 30. So the magnitude of the impedance is 30 ohms and the angle is minus 30 degree. So the power factor will be cos of this angle. So the cos of minus of 30 degree, you will get 0.866, which is the leading condition, and this value. So you can determine the power factor by either values of the voltage and the current or from the load impedance. Sometimes you will be given the phasor value of the voltage and the current. Sometimes you will be given the instantaneous value. So you can determine the power factor from any aspect. Now, the next part of the question was, what type of impedance do the series connected load have? So the load impedance can be modeled, because the value here, if you see of the load impedance in rectangular coordinate, Cartesian coordinate system we are getting, it is 25.98, that is the real part, and the imaginary part is 15 ohms. Okay. Now from there we can say that 25.98 is basically a resistor, whereas the capacitor value, because here you have a negative sign which indicates that this 15 ohm is coming from a capacitor. So the capacitive reactance is equal to minus of 15, which you can write at minus of omega c, because you know that the capacitive reactance is equal to 1 by omega c. Now the frequency you will be getting from here. What is the frequency? So frequency is equal to 100 pi. So 100 pi is basically is omega is equal to 100 pi. Then if you can substitute here what is the omega, Xc value you have already been given from the load impedance. So you can determine the capacitor, which is equal to 212.2 microfarad. So basically the Z is comprised of one resistance and one capacitance, which is a series connected load. The resistance value is 25.98 ohms and the capacitor is 212.2 microfarad. This we have calculated. Next, we will introduce one new term, that is complex power. Now, complex power is very important for the power system engineers. because it contains all the information regarding the power which is absorbed by a given load. So what are the different terms that we can have? We can have a real power P, which is the average power. We can have a reactive power Q, and we can have the apparent power, that is the product of voltage into current, denoted by S. Till now we have studied heat here. So one of the term, if we are given, it is very difficult to find the other terms or all the information. So we have introduced a new term, which is the complex power, which will contain all the information of the power for a load, and the load is AC. So given the phasor of the voltage and the current, we can write the complex power S is equal to half of VI conjugate. Okay, this we have already derived it in the previous lecture. So the complex power is equal to half of VI conjugate, which can write in the form of V RMS into I RMS conjugate. We are putting this conjugate sign over the current to take care of the angle between the voltage and the current. Okay, so V RMS, we can write it in the phasor format as the angle and the magnitude, and I RMS also we can write it. Now, the complex power S is basically the product of the RMS value of the voltage and the current with the angle. This is coming the apparent power. So the product of voltage and current is the apparent power. So we are introducing a new term, which is the complex power. These we can break up into the real term and the imaginary term. So this is the real part and this is the imaginary part. So we have two parts here for the complex power. So the impedance, which is the ratio of voltage by current, we can write V RMS by RMS and the angle theta V and theta I. So the complex power S is equal to I RMS square into Z, because the current which is flowing here is basically I RMS we can think of, and this is the load impedance. So I RMS square into Z. So we are not dealing with resistance now, we are dealing with the impedance Z, because this is a AC load. So I RMS square into Z will give you the complex power, or V RMS square by Z will give you the complex power, or otherwise V RMS into I RMS conjugate will give you the complex power. So we can use any formula for determining the complex power. Since the name complex power is given, it will be a complex quantity with a real term and the imaginary term. Now let us look into the different power concept that is there for. One is complex power, real power and reactive power. Complex power is denoted by S, real power is denoted by P, reactive power is denoted by Q. Okay, so we have seen that the complex power S is equal to I RMS square multiplied with Z. Now this Z is the load impedance, which we can write as the real part is resistor plus J times the reactive part as X. So I have substituted the impedance as R plus JX. Now this is a complex quantity which we can break up into two quantities. One is the real part, another is imaginary part. So the real part of the complex power is basically the real power. The imaginary part of the complex power is basically the reactive power. Then if we are breaking it, we'll get I RMS square into resistance, which is similar to the DC, that is I square R, will be the real power. Now real power is given by the other name, that is average power, true power, useful power. So any name you can use it for the real power, either average, true or useful. Reactive power is the power which is I RMS square into X. So we can write this one as I square into X, where current is the RMS value. So X is basically the reactance, which can be either the inductance or the capacitance, or the cumulative sum of inductance and capacitance. Now these power of real power and reactive power we can break up into two quantities. What is the difference? Here you have the cosine difference of the voltage and the current. Here you have the sine difference of the voltage into current. Otherwise the magnitude remains the same, that is the product of V RMS into I RMS. So this is coming from the apparent power, V RMS into I RMS. Now let us discuss what is real power and how it is useful to us. The real power is basically the average power. The unit is given in watt and it is delivered to the load. It is the useful power or actual power which is dissipated by the load. So when we say that there is a load which is AC quantity Z, it is consuming a power of 50 watt, then this watt is basically the real power. Okay. Now the reactive power Q, which is the measure of the energy exchange between the source and the reactive power of the load. So your source is basically AC in nature and you have the load Z, which is comprised of two component R plus JX. Now these X can be either inductor or a capacitor. So there will be continuous flow of the energy to and fro because of the AC cycle. So you will be having the AC cycle, so there will be continuous flow of the energy. So this power which is flowing between the source and the load, that is known as the reactive power, and it is coming from the reactive part of the load. The unit is given in volt-ampere reactive. Now, for example, if I'm having a load Z and it is said that the load is absorbing a power of 100 volt-ampere reactive, then this is the reactive power information given. Sometimes in the problem, the term power is only used. We do not use the term real or reactive sometimes. Why? Because we can see the unit, that is in watt or volt ampere reactive. By seeing the unit, we have to decide whether the power is the real power or the reactive power. If it is said that 50 watt, it means it is the real power. If it is said 50 volt ampere reactive, then it is the reactive power. So we do not use the term real and reactive always. We use the term power only. Now, since the load impedance Z can have the component, one is resistance, we can have impedance and capacitance. So this is the real part R and this is the imaginary part X. Okay, so R plus JX. We can have either inductor or a capacitor, or we can have combination of inductors and capacitors. If the reactive power is zero, if the complex power S is equal to P plus JQ. If the reactive power is zero, we can say that the load is entirely resistive. There is no reactive component and it is a unity power factor. Why unity power factor? Because the angle difference between the voltage and the current will be equal to zero. You know that in a resistor, the voltage and current are in phase with each other. So unity power factor, the reactive power is zero. Whenever you have a capacitive load only, then the reactive power will be less than zero. If you have an inductive load, then the reactive power will be greater than zero. Now, concept of leading and lagging power factor, which is lying between 0 to 1, will come from here. If the reactive power is less than 0, we can say that leading power factor condition is there. If the reactive power is greater than 0, we can say lagging power factor is there. So if the power factor is given plus minus some quantity Z, I will take some other quantity, that is L I can take. If we have the plus sign here, that means we have the leading power factor condition and the reactive power is less than 0, so the load is capacitive. If we am having a negative sign here, then it is a lagging power factor condition, it is an inductive load and the reactive power will be greater than 0. Now coming to the power triangle. So we know that the complex power S can be written as the real power P plus J times, that is the imaginary times, the reactive power Q. So if I am having one power triangle which is a right angle triangle whose base is given by the real power P, the height is given by the reactive power Q, then the hypotenuse of the power triangle we will be getting as S, that is the complex power. The theta, which is the angle between the real power P and the complex power S, is known as the power factor angle. We have given the definition power factor is equal to the real power P divided by the complex power S. So here from we can find out the angle theta is basically the angle which is making the hypotenuse with the base. Okay. Similarly, The real power can be substituted to resistance, the reactive power can be substituted to reactance, and the complex power can be substituted to impedance. Now here we are taking impedance magnitude because theta is already taking care of the angle. So we are dealing with only the magnitude of the impedance. Okay, so we can use this triangle concept to solve many problems related to power. So this is known as the power triangle and this is known as the impedance triangle because we have R, X and Z. So it is impedance triangle. Now the power triangle, if we are giving in terms of the real value on the x-axis and the imaginary value on the y-axis, then on the real part we will be having only the real power, that is the useful power or the average power. This is dealing with the resistance R. The part of the height of that is the imaginary part, can have a lagging power factor or leading power factor. We know that if Q is positive, it is lagging, and Q is negative, it is leading power factor. So this is dealing with the inductive load and the capacitive load. So you will be having here, you will be having one inductor and here you will be having capacitor. The complex power S is basically the angle between P and the theta. This angle is between the real power and the complex power. So theta V minus theta I. The angle between the voltage and the current, which is the power factor angle, depending upon if the load is lagging in nature. If the load is leading in nature, then the complex power will come downward here and you will be having the reactive power like this. So this is the power triangle which is dealing with all the powers: real power, reactive power, complex power and the power factor angle. Now quickly revise all the formulas that we have studied for the power. Complex power S is given by P plus JQ. P is the real part which is associated with the resistance and Q is the reactive part which is denoted in terms of the inductance or the capacitance. I can say X. Here you will be having R. Complex power S is Vrms into Irms conjugate. Vrms Irms conjugate, we will be having one angle, that is the power factor angle, the angle between the voltage and the current. Apparent power is the magnitude of the complex power. So Vrms into Irms, that is the magnitude of the complex power, is the apparent power. Unit is in volt-ampere. So it will be under root of P square plus Q square. So you have given the complex power P plus JQ. If you take the magnitude of S, that is under root of P square plus Q square, that is the apparent power. This can be written as the product of Vrms into Irms. The real power, that is given in watt, is the real of the complex power, which is complex power S. This is the apparent power here, the magnitude, cos of theta V minus theta I, the angle difference between the voltage and the current. The reactive power, whose unit is volt-ampere reactive, denoted by Q, is the imaginary power of the complex power S. Now here you have the magnitude of S and sine of theta V minus theta I. So if the cosine is used, you will be getting the real power. If sine is used, you will getting the reactive power. Power factor is the ratio of the real power by the complex power S. We can write is cos of theta B minus theta I. If I am writing here cos of phi, so phi means the angle between the voltage and the current, and that is the power factor. Power factor value will be lying between 0 to 1. 1 indicates unity power factor and 0 indicates the power factor which is entirely reactive in nature. Between that 0 to 1, you will have either the lagging power factor or the leading power factor. So we have covered the concept of the complex power, apparent power, reactive power. Now there is some methods by which we can have the power factor correction, that is to reduce the reactive power, that we will study later.